So what I will do is, okay, so again, this is very stereotypical. This is like a textbook experiment or textbook use of this thing, is that assume that these registers or the hashes contain within. Right now they should not contain anything. Assume that they represent the state of your system. So they're all empty. I mean, they're some are -1, but you can't actually use them. Assume that they represent the state of your system. Like you measured your kernel, you measured a whole bunch of stuff, and the hashes actually represent that. So what you can do with the TPM is, what you can do here is that you can encrypt a bunch of stuff. And you can say that I'm encrypting this, but this can only be decrypted on this TPM if the hashes within match. At the time of decryption, they match what they were at the time of encryption. So something like this, that I can say, so I'm saying, sealed, this thing is called sealing. Seal this thing, bind it to this register number, and so I have this blob here, this is armored. And, well, you can try to unseal it. It works. Now, what this extend PCR does is, so let's look at those registers again. So let me extend a PCR, which means that I'm generating an event or something. I'm just saying that here's the event, it's a string. And extend the PCR number. So there's a hash in there now. And let me try to unseal it again. So it says wrong PCR value. What can you do with it? Well, Microsoft is doing the BitLocker, is that what it's called? Some kind of drive encryption thing. We can actually do that on OS X too, in more ways than one. The firewall talk that we had, it gave me some ideas, but even if you don't use firewall, OS X has another. See, they're very nice with filters. They don't give you APIs, but they give you a lot of filters. So one thing Apple gives you is a block storage filter, which means that you can write a kernel extension and you can sit atop a block device, whether real or virtual. And then you get to see everything that passes through. So you get to possibly rewrite the contents of every block as it passes through. So you could use this with that to create your own disk image framework if you want. That thing is quite well supported. The other thing you could do with this is, again, it's kind of a stereotypical example. So if you go, let's see if I have network here. Okay, so this is how I log in. If you go in my .sh directory, you will see that I have this thing called authorized keys. What does it contain? It contains what you would expect, except that in this case, it's not like a software-generated public key. It's something that this key pair was actually created inside the TPM. The private key was spitted out as a blob. Mess with my terminal. So, what if, okay, so here's a trivial implementation of RSA sign from OpenSSL. All it does is, instead of using what it would do in software, it just offloads that work to the TPM. So when the key exchange is being done during the initial SSH handshake, so what I'll do is I will interpose this, I'll LD preload equivalent this library in my SSH connection here. And so all this does is if I give it an argument, so what is the argument? So the argument is that you have to load this key into the TPM first. So I have a key handle, and then I can say login. So it logs in, and well, within reasonable limits, this login is quite secure because, well, in a way it couldn't have been made other than from this machine. Because this RSA signature couldn't have worked except inside this TPM. At least that's the idea. And no, there's no secret here. I mean, there's no like, oh, but it breaks under those circumstances. It's actually quite nice. So, where's my mouse? Okay, so so maybe I'm giving the impression here that I really like this and there's nothing wrong with these technologies and all the privacy concerns are unfounded. Well, that's not really the case because it looked like Palladium would disappear and Microsoft would, you know, they just thought it's a bad idea. It was really badly received. But so Intel has La Grande. I think I've heard people here talk about it, so I'm assuming that you know what La Grande is. The TPM is just one of the components in La Grande. I mean, it actually extends a lot of stuff. So if this is your PC platform today, with La Grande it's a lot. In fact, it really is trying to create this reference monitor thing that I mentioned earlier, because what will happen here is that you get essentially ring -1, and you run some kind of like this tiny hypervisor kernel inside this ring -1. And so a common argument today is that, well, what are you going to do if if iTunes DRM? You're eventually going to play some audio and it's going to go through your sound card. I can always capture it in flight. Or keystrokes, I can always log your keystrokes. So no matter how you tighten something, eventually I'm going to capture it. So this thing's goal is to make the impossible really hard. And they're doing some crazy things, like you will need this special USB keyboard, which, so Windows XP runs as it would. This hypervisor runs in ring -1. If there's a super secure app which runs in, like its own virtual machine, and the virtual machine is secured using the TPM, and so is the graphics card. I mean, so is the output and the input. And the keyboard will actually negotiate a key with the software, and the hypervisor will assist in this. I mean, who will program for this and why? Well, let's see. But Microsoft, so every time it looks like they're going to use it and it's just around the corner, they back off a little bit. So this is the so-called NGSCB. And I think it's a bad idea. I think it's simply a bad idea because it's really hard to program for. It's going to stultify innovation in the sense that, like, when you use applications, you want to use applications that people like to write. You don't want to use applications that are pain to write, because then most of my processing is going towards these applications and antivirus and this and that. But anyway, so these are just some random thoughts. I found this somewhere, and I think we are out of time. Do I have time to show you the demo I mentioned? Okay, so a quick rundown of that the demo I mentioned, because since we've been talking about these mock interfaces in VM and processes. So, like I said, and the point of mock is that most things are IPC based. You want to allocate some memory. When you do a malloc, malloc eventually results in mock IPC, which says, please map this memory into my address space. It can just as easily result in an IPC that says, please map this memory in that guy's address space. So like I said, there is no difference. So OS X people want to do funny things like these. Bear with me while I type my password. So something like this. It's quite stupid, but or something like this. And I really like this because, you know, this continues to work. No. But this is not the interesting part. This is hardly the interesting part, because you show this to people who write all those fantastic UIs, they're like, huh, so what? And then I have to tell them, do you realize how this was done? So well, all these transitions and all these effects, they're actually supported by the Windows Server. It's the first-class API that only Apple has access to. All these funky keynote transitions, they're also, like, there's actually an API but you can't use. Now, well, if you knew how to use this API, let's say you reverse engineered, well, you could use them, but still in your own programs. The reason is, well, implementation-wise, you first need the window ID of the window in question. The window ID is just a number, but it's just a number like a file descriptor is a number, which means that just knowing the number is not enough. You actually need these rights. So we were talking about these send rights and receive rights. So where are the rights going to come from? So really, the only way I can do this is if I am this task, which means I'm Safari. So it means it's really easy to do it in your own programs, but you can't do it in other programs. So how do you do that? Well, we use our... I'll play this while we talk. Okay, so the way we do this is, we talked about threads and processes. So what I do is, I can suspend a task remotely. When I say remotely, it means like you don't have to be that task, you just call a mock IPC function. And so I suspend this task, which suspends all the threads within it. Then I suspend all the threads within it, because when I resume the task, I don't want them to run. Then I select one thread. I mean, everybody is going to have at least one thread, so I just select the 0th thread, the first thread. Then I use another mock IPC function to actually suck the thread state out of this. So it lets you do that in all the registers, just in a lump sum. I stash them somewhere else. Then I use this remote memory allocation function, because memory allocation is uniform, and the other process doesn't matter. So I allocate a new chunk of memory for this guy, and I move its stack pointer over there. Then, but if you're thinking that you just inject some code and it's going to work, well, actually no, because many of the library functions, they want a valid pthread context. So you can't just have a mock thread. You need all the pthread user state too. So what I do is then, and then I allocate another chunk of memory where I'm going to actually put some code in. This code does nothing but allocates it, but instantiates a pthread. And once I'm done with this, I have my stack set up for the pthread, I have the instruction pointer set up, then I resume just this one thread. So if a task is suspended, all threads are suspended, regardless of their individual suspend counts. And then I resume the thread and resume the task. Only one thread is running, my thread, the one I hijacked. And then I do what I want within it. And well, how do I know? Because I have to set it back. So how do I know that it's actually done? Well, another thing you can do with mock ports is